Today on Macaulay Math, we're talking one-sided limits. Intro. Hello, I'm Professor Macaulay, and this is Math 200 Calculus 1, lesson number 4 on one-sided limits. Our goals for today, we're going to understand the definition of and how to apply continuity. We're going to determine the continuity on a closed and open interval. We're going to determine a one-sided limit on a closed interval, and we're going to apply the intermediate value theorem. Let's start with the definition of continuity. A function f is continuous at c if the following conditions are met. The first condition, if f of c is defined, so if you have a value for x and you plug it into the function and you get a real number out, then f of c is defined. If the limit exists, and so if you have a limit as x goes to c of f of x, if that exists, that is the second condition. And finally, the third condition, if the limit as x goes to c of f of x is equal to f of c, then you have continuity at a point. Continuity on an interval. First, before we get to continuity on an interval, let's review some interval notation. And this is certainly not an exhaustive list of examples, but real quick, let's start with an open interval. And this is the values of x from a to b, not including a to b, but all the values in between. So inequality notation for that would be a is less than x is less than b. And so a graphical representation, we would have all of the values between a and b, but not including a and b. So it looks something like that. If they use brackets, we're talking about a closed interval, and that's similar to an open interval, except with closed intervals we are including the endpoints. So the inequality notation for that only changes in the fact that we add the equal to the less than notation. And as far as the graphical demonstration goes, instead of open circles at a and b, we'll have closed circles at a and b, and we'll be talking about everything in between. All right, and finally, this interval here has towards negative infinity. Remember, negative infinity is a concept, not a number, so you could never actually include negative infinity or positive infinity for that matter. But this is going to be a compound inequality, and because we have a bracket at a and another bracket at b, it will include both a and b. So what we'll have here will be values of x that are less than or equal to a, or values of x that are greater than or equal to b. And what that'll look like is we'll have another closed circle at a and a closed circle at b, and we'll be talking about all the values less than a or all the values greater than b. All right. So a definition, a function is continuous over an open interval a to b when the function is continuous at every point in the interval. If a function is continuous over the entire real number line, it is said to be everywhere continuous. Second definition, a function is continuous over a closed interval a to b if the function is continuous on the open interval and the following limits are true: that the limit as f of x goes to a from the right hand side is equal to f of a, and the limit as f of x goes to b from the left hand side is equal to f of b. And we're going to be talking about what the notation for a with a superscript plus and b with a superscript minus is later on in the lesson. Discontinuity. If a value for a given function fails any of the three properties for continuity at a point C, then there is a discontinuity at that point. A discontinuity can be classified as a removable discontinuity, and this is a Macaulay definition. It can be filled in with a point. A non-removable discontinuity, and so there are two types of non-removable discontinuities: a jump non-removable discontinuity, and for my little extra definition in there, there is a finite distance between the endpoint, essential non-removable discontinuity, or an infinite non-removable discontinuity. That means that there is an infinity between the endpoints there. This is a quick demonstration of some point discontinuity. All of these discontinuities will occur at the value c along the horizontal axis. The first is removable discontinuity. We see that we will have a hole at x equals c, and that we could potentially fix this hole by filling it in with our pencil. These removable discontinuities are considered less severe than the non-removable discontinuities, and they are important since we will be using a property of them to evaluate derivatives later in class. The second discontinuity is a jump discontinuity, and it is named because there is a measurable gap in the function at the discontinuity. The final non-removable discontinuity is an infinite discontinuity. In the case shown here in the demonstration, we have an infinite discontinuity where there is an infinite gap at c. This is not the only example of an infinite discontinuity. For another example, we move to the Desmos calculator. Y equal to the sine of 1 over x. And this is another type of infinite discontinuity because the closer to 0 1 over x gets, the closer to both positive and negative infinity you get, depending on which side of the x-axis you are going towards 0. So what happens here is you'll notice it's close to 0, and the closer I get to 0, the bigger this number is going to get negatively, and so it starts bouncing up and down and up and down and up and down and gets closer and closer. And so even though we zoom in, we can see that it's starting to separate, but we get into this infinite loop of up and downs and up and downs and up and downs and up and downs, and no matter how close to 0 we get, we will never actually get to a value. And again, at 0 we will have an undefined. So even though this bounces between 1 and -1 forever, we still have a non-removable infinite discontinuity. So, another example. Alright, so let's discuss the continuity of the following function over its domain. And so this function here, if we look at this, we can see that there are potentially two discontinuities. So there are divisions by 0 at x equals -2 and x equals to 1. All right. So I have discontinuities at x equals -2, and I have another discontinuity at x equals 1. Well, let's go back to Desmos here quick, and let's clear this out, and let's type in that equation. So let's go y equals, and then we'll go parentheses, and then on the top, x plus 3, and we have x minus 1. And then on the bottom, x plus 2 and x minus 1. So clearly, we can see that at x equals -2, we have an infinite discontinuity. At x equals 2, we have an infinite discontinuity. But at this 1, we should also have a division by 0. So if I go exactly to 1, you can see that it says that at 1 we have an undefined. So technically, even though Desmos doesn't show it, this is going to give us a removable discontinuity. So we know, we can say that this function is continuous on the open intervals from negative infinity to negative 2 unioned with negative 2 to positive 1 unioned with 1 to positive infinity. There is a with a non-removable infinite discontinuity at x equals negative 2 and a removable discontinuity at x equals to 1. So how do I tell the difference between a non-removable discontinuity and a removable discontinuity? Well, when you're looking at a rational function like this one is, you'll notice that I have an x minus 1 and an x minus 1 in both the numerator and the denominator. Since these two cancel out, the function actually only looks like x plus 3 over x plus 2, because for every value of x other than 1, these two are going to be the same value, so you get 1 over 1. When x equals positive 1, you get a 0 in the denominator, so the function is technically undefined. But again, because I can cancel these out for all the other values, I get a removable discontinuity. Since this factor x plus 2 does not cancel with a factor in the numerator, I get a non-removable discontinuity. Notation for left and right-sided limits. So the right-sided limit says the limit as x goes to c from the right-hand side of f of x, and the left-sided limit is notation the limit as x goes to c from the left-hand side of f of x. Properties of continuity. The following functions are continuous on their domains. Polynomial functions are continuous on the real numbers. A rational function is continuous provided that the denominator is not equal to 0. Rational functions are continuous provided that the denominator is not equal to 0. Radical functions are continuous provided that the radical does not produce an imaginary number. And trigonometric functions are continuous on their domains. Next, here is the definition of the intermediate value theorem. If f is continuous on a closed interval a to b, and f of a is not equal to f of b, and k is any number between f of a and f of b, then there is at least one number c in the closed interval from a to b where f of c is equal to k. So here we have a function, and along the x-axis from a to b, it is continuous. We can clearly see that f of a is not equal to f of b. So now if we choose a value k that lies between f of a and f of b, there must be some value c between a and b such that f of c is equal to f of k. As long as k lies between f of a and f of b, c will lie between a and b. Some additional examples: find the limit if it exists. If not, explain why. And so here, this limit says find the limit as x goes to 3 from the right-hand side of 2 over 3 plus x. This is a rational function, and if I were to plug in 3 in for x, I can do this through direct substitution. So through direct substitution, we can say that this limit is going to be 2 over 3 plus 3. 2 over 6 is 1/3. In this second expression, a direct substitution creates an indeterminate form. So we have a problem. So I can't plug it in. So the first thing I'm going to try is I'm going to try to factor. Alright, so I haven't taken the limit yet. So the limit as x goes to 4 from the right hand side, I've got 4 minus x over, well, this is a squared minus b squared. This is a difference in squares. So I can factor that to x minus 4 and x plus 4. Alright. Well, let's talk about this x minus 4. If I factor out a negative 1, I can go the limit as x goes to 4 from the right hand side, and I can go negative 1, and then I'll have negative 4 plus x all over x minus 4, x plus 4. And you'll notice that these two things will cancel out. Alright? And so the limit as x goes to 4 from the right hand side will be negative 1 over x plus 4. And I can plug that in. That'll give me negative 1/8. Now if you're not sure, we can always go back to Desmos and take a look at this thing. So if I go back to Desmos, I clear out what I had here, and I type in, and let's just use function notation this time to change things up a little bit. F of x is equal to, it'll quantity 4 minus x divided by x squared minus 16. And so again, what we're doing here is they are asking us to come in from the right hand side. So we're coming into 4 from the right hand side, and we get this value right here, and that looks pretty close to negative 1/8. So we feel fairly confident with that solution. Alright, find the limit if it exists. If not, explain why. Alright, so now I've got this delta x here, and delta x, we're going to see a lot of delta x coming up here soon, so it's good for us to discuss what that means. Delta x is just another variable, but they're not the same variable. So x plus delta x, these are not like terms, so we got to keep them separate. So we're going to let delta x go to 0 from the right hand side. Well, I've got delta x in the denominator, so direct substitution is going to give me an undefined. So here's what we're going to do. We're going to try and simplify some of this stuff first. But remember, when I square a binomial, I'm going to have to multiply that out. So we're going to simplify first. And so this is going to be equal to, and again, I haven't taken the limit, so I still have to write the limit. And so x plus delta x quantity squared, that thing I'm going to have to multiply out, and when you multiply it out, it turns into x squared plus 2x delta x plus delta x quantity squared plus x plus delta x, and then I have to distribute this negative to both terms, so I have a minus x squared and a minus x, and that's still all over delta x. Well, again, we're going to simplify because we get some things to cancel out here. Notice I've got a positive x squared and a negative x squared. I've got a positive x and a negative x. So those cancel, and I'm left with the limit as delta x goes to 0 from the right hand side of 2x comma delta x plus delta x quantity squared plus delta x, and that is all over delta x. Now I can divide out a delta x from each term. And if I do that, I'll get 2x plus delta x plus 1, and it would be all over 1, but we wouldn't do that. Now this is a new function where all of the limits are the same as that function with the exception of delta x equaling to 0. Therefore, I am allowed to evaluate this thing through direct substitution. Now this time, because I'm evaluating the limit, I don't have to write the limit. I'll get 2x. I can have that variable. Remember, we're letting delta x go to 0, not x, and these two are different variables. And then I let delta x go to 0, and then I have my 1, and so my limit here is 2x plus 1. And so this is our first limit where we actually have a variable expression, and that's okay. All right, let's talk about the following one-sided limits. And for us to do that, at first I'm going to show you a Desmos version of that. So let's look at this piecewise function via Desmos. And I've written this in Desmos notation, and we can go over that in class. But what they want us to look at is they want to know what is the limit of f of x as we go to 3 from the right hand side, and what is the limit as we go in from the left hand side. Okay, well, let's take a look at that. If we start over here and we continue to go in until we get to 3, now even though we're not including 3 in this particular one, the values of x as we get infinitely close tend to go to 1. It is a constant function. So as I come in from the right hand side, and again, we could use a direct substitution here, it is just going to be 1. And as we come in from the left-hand side, let's take a look at that. As I come in from the left-hand side, it looks as if this function is going towards 2. And again, if I do a direct substitution, this is a polynomial expression. 2 times 3 is 6, minus 4 is 2. And so we get a 2 for that limit. So the right and the left-hand sided limits in this particular case were not equal. Well, that's all I got for today, folks. So, the Star Wars fun fact of the day. During the filming of the trash compactor scene in Star Wars: A New Hope from 1976, Mark Hamill had to hold his breath so long underwater that he burst a blood vessel in his left eye so badly that the final shot had to be filmed from his right side, as not to show all of the blood in his right eye. And you can see here we are showing his left side and his left side there. That's all I got for today, folks. Goodbye.